Today we will start with the bioinstrumentation. So I think it's a little late. If you have a problem listening, please use the chatting to respond to me. All right, so we will discuss about bioinstruments today. And first, let me introduce about this bioinstruments. So what is bioinstruments? This is a device for measuring biological system, biological information. So let's consider when we first go to the hospital, and what do we see in the room, in the doctor's office. So this is an example of the doctor's office, so that you can actually see here a lot of instruments you can identify. There's a bed, but there are like various kinds of instruments, which is originally for the physician to assess the patient with the various kind of biological data. So especially vital sign is very important to understand. So what are the most important, excuse me? Okay. What are the important biological signals, which is vital? So that we call vital signs. You can consider it as simply the body temperature and blood pressure and heart rate and various things. So the first thing the doctors will see the patient, and to understand the status of the patient is vital signs. So let's go through a little bit of those. So temperature, of course, we write it T, but we are talking about usually degree Celsius. And blood pressure is very important for the status of our cardiovascular system. And that unit of always, whenever we discuss about physical or biological quantity, it's very important to use proper note and use proper units so that we can communicate properly. So blood pressure is millimilli Hg. And also another thing the doctors will watch you over is the heart rate. So that's usually now you have this device which can automatically spit out these data. So heart rate or HR, or we call it pulse rate. So usually the unit is the number of pulse per minute. So that's how we actually use it. And the other, is about respiratory rate. So the breathing rate, okay? So that's also in 1 minute, how many breathings you're performing is respiratory rate, or RR. And in addition, if the patient status is it's more in critical condition, we also can have additional vital signs, which is the oxygen saturation. We'll discuss the instrument, how to do this. And also sometimes if the patient is diabetic or having issue with the glucose, then blood glucose. And so oxygen saturation in percent, glucose in milligram per deciliter. So when we talk about this, the doctors see the patient's vital signs and having a general assessment whether the particular patient's vital sign is within the normal range in the population. So we define a concept of so-called the normal range, and or we call it reference range. It does not mean that if you are out of this range, have to be abnormal. No. So here the normal means it's over the general population. So it's important to understand. For example, I have a heart rate actually pretty low, and blood pressure is pretty low. That doesn't mean that I am in an abnormal. The normal range is as a reference for doctors to understand what's going on, because now we have a bunch of plenty of bioinformations, and these data are available. We are moving into not just talking to normal range, but more of a personalized bioinformation. So if, like, for example, like me, I usually have a lower blood pressure, and that's normal for me. And what's maybe more important is the traces of history of my blood pressure. If it's getting abnormally, strangely higher, then it can be a more issue. So this is now changing. Instead of putting a normal range in the general population, rather, I think we are moving towards a personalized bioinformation. Okay, but the normal range is the range of values for a physiological measurement in healthy persons. Okay, so at least it's important to know what are the general normal range of this. Let's see. So here's adult vital signs of normal range. So there are a number of acronyms which you are supposed to understand. So heart rate is about 60 to 100 pulses per minute. As I said, 1 hertz is kind of defined as probably defined as our heart rate. So 60 is per minute means 1 hertz or 1 time, 1 pulse per minute. So about 60 to 100 is a normal range. And respiratory rate, you can actually check with your watch and see how many times you are breathing over a minute. So that's usually 12 to 20, which is a normal range. And in terms of blood pressure, we already discussed about it before. And when the squeezes of the heart, so systolic blood pressure has to be below 120, usually 80 to 120 as a normal range. And what about diastolic blood pressure? That is about less than 80 mmHg. And also very important vital sign is the temperature. And temperature can vary from where and how you measure it. So it's in the temperature case, there are different kinds of measurement. For example, temporal artery here, and tympanic temperature, which is your tympanic membrane. Through this, it's much more convenient nowadays. And that temperature might be different, the temperature through oral. So, you know, like many thermometers in the past was oral temperature. And people say more accurate, which means the temperature is closer to the body core temperature is a rectal temperature. You see that these can be a little different. And also this axillary temperature. All right, so that's something normal range we have to know in general. And then what affects the vital signs, why vital signs are important is because of the factors when you are in some certain type of condition or under the disease condition. So for example, of course, when there's a fever, your heart rate goes up, respiratory rate goes up, and your temperature goes up. And probably I picked some of this important one. For example, acute MI. You guys know MI is myocardial infarction. So acute MI, when there's a myocardial infarction, which is usually blockage of coronary artery, and it kind of debilitating the heart function, then the heart rate comes down. While you have to compensate, so you increase your respiratory rate, and because of the function of the heart, let's say left ventricle is compromised, so your systolic blood pressure goes down. And when it becomes a more critical condition, and you can reach to CHF or congestive heart failure, and that condition is more critical. And it actually has a kind of emergency. So congestive heart failure, your heart rate goes up, your respiratory rate goes up, even systolic blood pressure, early stages goes up, and temperature goes up. So these vital sign changes are indicative for the physicians to recognize and assess the status of the patient. So for other example, you know that when you are exercising, then you have to, you need a lot of oxygen need, and so that you increase your heart rate, increase your respiratory rate, and your heart pressure, systolic blood pressure, and temperature too. And there are other conditions such as H&H, which stands for hemoglobin and hematocrit. So your blood, it's like anemia though. Hemoglobin and hematocrit is low, then you have to maintain your need for oxygen, so increase heart rate, respiratory rate, while in this case, systolic blood pressure is not that high and temperature goes down. All right, so that's some of the example, and I want to discuss about bioinstruments more in a modern society. So as we just observed in this modern healthcare system, in the operating room and emergency room, and of course doctor's office, and they are now full of these instruments. And thinking about economic point of view, this medical device industry is one of the largest and fast growing industry in modern economy. So like you've heard about medical device companies, and also you've heard about pharmaceutical companies. And now what are big trends is now when in the past you have to go to doctor's office, you have to go to hospital to do some precise measurement. Now things are rapidly changing, and that reflected by this POC or point of care testing devices. So what that means is medical testing at or near the site of patient care or like at home. So that's, I want to show this picture of medical devices that can be used at home environment. So this is really rapidly changing. So I'll give you some examples. For example, disposable device, such as a pregnancy kit you can use at home in very convenient way. And handheld device for, let's say, many information such as glucose measurement. I think those can be used with a very simple handheld device. And monitoring system for even like those who have high blood pressure, now they can have this blood pressure meter at home. And like these, many of the devices, the whole world it's moving towards making this device smaller and portable and cheaper, so that actually you can use it at home environment. So that's has been a big change. So this requires us to understand about these bioinstruments. So what are the bioinstruments? Bioinstruments is a sensor or actuators that are used in medicine or biological research. So because you know what instruments means, because it has bio, it usually means that it's connected to a bio, which means a living system. So bioinstruments you can define as acquiring and processing and displaying or transmitting the information of biological data. And in biomedical engineering, what kind of areas which is using these, using or developing these instruments, and some of the examples include bioelectronics. So, you know, electrical engineering, electronics, you know that, and when it's bio. So, for example, we are dealing with biological electrical signal. For example, cardiac monitoring. And you remember ECG, electrocardiogram, and those can be related to bioelectronics. And what about biomechanics? So it's a mechanical engineering, but it deals with the biological signals such as tissue testing or making like artificial hip and joints. And other example is bio-optics. So we can use optics usually for imaging or assessing, analyzing the information in the biological tissue. So for example, optical imaging for diagnostics. One good example would be endoscopy. So we can use optics to visualize our internal body parts, which can reveal some the presence of disease or screening for disease. And more, another example is medical imaging in general. So we can utilize the imaging device such as MRI, magnetic resonance imaging, or PET, positron emission tomography, or CT computed tomography, which will have like amazingly changed our understanding of human disease, because it actually can reveal the inside of our body and also reveal if the presence of lesions or disease. So what's the most important keys to successfully engineering of this bioinstrument is, we have, from the industry point of view, we have developed many of these instruments. Now the application is for bio or human medicine. Then the most important thing for us to understand is the object, the subject's condition, especially the physiology of the system. And of course, whenever you consider about instruments, you have to clearly understand what are the variables or you are measuring. And also, you guys are, most of you guys are involved in research, and you will be using many of the instruments. And I always say the most important part is don't just consider the instrument as push the button and get the number. Like, don't consider that way. Whenever you are using an instrument, you have to know the limitation of the instrument and the component and the physical or chemical, biochemical principles behind the instrument. So the working principles is very, very important, because if you are not going to be just become a technician, you have to know what's going on underneath. So the limitation of the instruments, especially this is important when you are involved in research or anytime. I'm sure you go out, you become a leader, and you have the eye and understanding of what's going on. And so don't just trust the data which is spit by the instruments, because every instrument has its limitation and you need to know the working principle behind. Okay, so regarding this bioinstrument, let's talk about general components. So first, you can consider the components of bioinstrumentation as a simple way. So you have this sensor, and sensor has an input or measurand, and sensors will generate a signal, and that signal will have to be processed and giving as an output through the receiver as a display or certain type of a signal that can be interpretable. So the first input of quantity intended to be measured, we have a terminology for that. Okay, I think for this, Ichibom?
Yes, Professor.
Oh yeah, can you guess what that quantity? I don't see the face. Yeah.
Measurand.
Okay, great. Yes, yeah, that we call as a measurand. So for example, these measurements are pressure, temperature, and flow. So which means, for example, like our body, blood pressure, body temperature, or blood flow, or chemical concentrations such as glucose, or voltage directly our body's electrical system is producing voltage or current, can be a measurand. And then this goes into the sensor, and sensor, is a part of the instruments that detect the input, and that converts into a signal. Signals are mostly electrical voltage. So these sensors convert a signal from the input into a signal type. So that we call another way. Let's see, Song Young-gu. Yeah, can you guess what this is?
Transducer.
Yes, great. So you guys remember in cell biology, there are signal transduction cascade. So that transduce means change of a form of a, let's say some energy from one into the other form. So that we call transduce. So sensor is another way we call it transducer. And usually the signal is weak and noisy. So we usually have to process it through this signal processing. So further modification of signal by amplifying weak signal or filtering out noise. And also there could be multiple inputs and you can extract signal of our interest. And at the end, we have an output display or recording so that we can present interpretable message to the interpreter as to us or physicians. So with that, I want to discuss a little bit of the instrument operational modes. So when we are measuring signal, so always direct measurement would be better. And that doesn't necessarily mean it's good for the patient. For example, let's say I want to measure brain wave, okay? So electrical signal of the brain, the best way is you put the electrode into the brain parenchyma, okay? So for the signal point of view, it's better to reach the electrode directly to the brain, but that requires a surgery or invasiveness. So it's not necessarily for patients. So that are the limitations. So because the brain is covered with the skull, cerebrospinal fluid, and scalp. So usually the signal you are measuring can be very, very weak or noisy. So that is a problem. So for example, that we call as a direct or indirect measurement. MEA or multi-electrode array, microelectrode array, as you put it into directly to the subject or sample. So that's direct and invasive. It gives a good signal, but it's invasive. Another example is fMRI. Is the fMRI try to measure a neural activity, a local neural activity usually in the brain. And so the good thing is this fMRI is not invasive, but you have to understand the limitation of this fMRI is, in fact, it's not directly measuring the neural activity, which we believe it's linked to the hemodynamic changes and locally. So that we have to understand that these are indirect measurements. And another aspect I want to discuss is the data acquisition itself. When we say the vital signs, such as let's say heart, let's say ECG signal, majority of the signal are continuous and time varying signal. And that continuous signal, we call it as a analog data. So most of these are analog data, but this, so these sensors, senses are analog data. However, most of the time, we convert the signal into our computer, which is digital. So most of the time, we are converting the signal into digital format for processing or transmission. What we call this as an analog to digital conversion or ADC. Okay, so that is something very important for us to understand, because in fact, most of the time we are sampling the signal over not continuous time point, but sample the time point, or we call it as a discrete time point. Not only this over time is discrete sampling, but also the level of signal is supposedly analog, but when we are getting it into our computer, we always have discrete level because we are dealing with a discretized data. So this is an example to show that, let's say, the blue curve is time varying signal, then we can't, or most of the time, we don't collect the signal unnecessarily often. So this is an example of this continuous, not continuous, discrete time we are collecting signal. And look at this black dot. This is the signal we are actually collecting to represent this blue original signal. And also this black dot levels will not be continuous, which are described next slide. So that when we call this discrete time as a sampling, and also discrete level amplitude, we call it as a quantized. So the y-axis level is in fact quantized. Okay, for this discrete time sampling, there is a hugely important concept to understand, and that is, the name is so-called Nyquist and Nyquist criterion. For those who are from engineering background, have heard about this and very important, or we call it as Nyquist-Shannon sampling theory. So this is one of the most important concepts for signal processing, but the implication is very simple. Okay, so what it means is, when you are sampling time varying signal, let's assume time varying signal can be decomposed into a sinusoidal curve. So you may have heard from Fourier analysis, Fourier transform, Fourier series analysis. Any continuous signal of can be fully reconstructed by discrete time samples if you sample it fast enough. If you're sampling it too slow, you may not reconstruct the original signal. But there comes this Nyquist criterion states that you have to have sampling the signal at least twice faster than the signal's own frequency, which is defined here as a bandwidth of f sub bandwidth. So if you are sampling at least twice more higher, then you can always fully reconstruct that signal. So this is an amazing insight and very, very important. And from this, we actually can have a guideline. So what if we don't meet this Nyquist criterion, then something weird thing can happen. Which weird thing is actually happening right now into your video, because I see you're moving like kind of strange way. And this is also kind of relevant to this. And sometimes even the way things change, the direction can reverse. That weird thing we call aliasing. And to prevent this aliasing, there's a guideline and an easy way to reduce or remove those. So that we call anti-aliasing low-pass filter. So let's say if your instrument has a sampling rate of 2 times bandwidth, let's assume. But in general, analog signal can have a vast range of frequencies, in fact. But high frequency are mostly noise, I guess. So then you can precondition the signal by putting a low pass filter, which is cut off at bandwidth of f before you sampling at 2 frequency of bandwidth. So this way you can ensure that you are properly sampling the signal. Okay, we'll get back to this again. So I'll give you just a simple example figure here. Let's assume the actual signal is a red curve, which is sinusoidal. Okay, what if your sampling is slow? What happens? So this gives an example. You look at this 1, 2, 3, 4, 5 black dots are actual sampling points. Then you want to reconstruct this with a sinusoidal, then you actually can end up with this dotted black line curved, which is distorting the signal. It's not representing the original signal. So this is an example of aliasing, or this happens when you do not meet this Nyquist criterion. I'll show this again next slides. But everyone should thoroughly understand this concept. All right, sometimes, many times you will like to see a real-time data, but some other times it may not be that absolutely necessary. So real-time signal processing can be essential when the bioinstrument having a feedback directly. Of course, it's always good, but sometimes maybe some delay is acceptable. For example, I want to see my blood pressure and I measure. I'm not that interested in my blood pressure changes over time in real time. So it may take maybe 5 seconds. They display my blood pressure. I'm fine with that. But let's say we are in the hospital during the surgery. I'm doing this procedure, and this procedure can affect the patient status. It would be better to know directly the vital signs in real-time monitoring. So in that case, this real-time operation would be more important. So here I want to discuss, before when I talk about Nyquist criterion, it's about temporal discrete time sampling. But at the same time, whenever we collect signal, we are digitizing the signal level, because we are using a discrete and trying to use as a little space as possible. So this shows demonstrate an AD conversion, analog to digital conversion, quantization error. What do I mean by quantization? So x-axis time, and the blue line is the actual signal. And however, as I said, we are sampling over time. So let's say this time we record this signal, and then this dot, this time we are sampling. But the actual, the level of signal is blue. However, we can only measure certain level. So for example, here, this black horizontal lines are the discrete levels we can collect. So how we collect the signal is we use this point to the nearest nearest level, which is this one. And this one, the nearest level is not here, but this one. So this is reported this digital level. So then you can see inevitably it occurs that there's a difference of this actual versus our recorded one. So that level change is due to the quantization of our signal collection level. So that's why we call this as a quantization error. Then we can say, ask a question. So what's the maximum quantization error in this general case? Then you can see this blue background. So if this point is like at the middle, we can define it as a higher one. So this is a maximum error can happen, which happen to be half of this discrete digital levels. So you can say what's the maximum quantization error. Of course, the more dense the levels are, the less absolute quantization error will be. And you can also ask a question about what's the resolution of this measurement system. And in general, we define the resolution as the differences between these digital levels. Okay, I hope this one makes a good sense to you. And so maximum quantization error will be half of the resolution. I'm sorry about the poor quality of the image, but I'll be explaining in detail. So now we get back to the aliasing inaccuracy. So that's what happens when our sampling rate is not fast enough. And that is based on this Nyquist frequency. The problem when we are not sampling fast enough, then there comes a phenomenon called aliasing error due to too slow sampling. And another example for here is, let's say the blue sinusoidal curve is the true signal. And let's say we happen to collect sample at least, let's say at this every half of the period, okay? So that is exactly here with the red dots. So the red dots are reported or leveled, but consider how you only see, you do not be able to see blue, but you only see the red dots. And how can you reconstruct this using sinusoidal? And that's only coming to these red ones. And you compare the period of blue and red one. So the red one's period from here to here. During the time, the blue one's 1, 2, 3 period has passed. So you are kind of already 3 times off the frequency of the signal, so which is completely wrong. And that we call aliasing error. Then the question is, how fast do you have to sample? And there comes the Nyquist criterion, and there's a 2 times of the signal frequency. And let's see why that's the case. So this is an example that aliasing inaccuracy. The top one is exactly when your sampling frequency is slower than twice of the original frequency. And you can see if you look at follow this black dot, you are definitely interpreting this a very, very slow signal. And then Y2F. So let's see if you're sampling exactly twice the frequency of the signal, and there could be different cases arising. So here, if you're sampling twice of the frequency, what that means is in one period of the signal, you are collecting 2 points, okay? So then if you happen to match the phase with the 1, 2, the top and bottom, during and this one period, you collect signal 1 time, 2 times, okay? And if you happen to meet the top and bottom, then you know the sampled signal has the same frequency. Oh, which is great, okay? What's the problem with this? But if you move this collection time by half of a quarter of the period, let's see what happens. Exactly the same period, but if you move it, it happens to meet over here. So you are collecting sample exactly the same level. So you lose, your signal is collected here is constant. And this happens when your sampling frequencies exactly twice of the signal. So you have to come back to think of it. So what it means is this is not enough. And if you are sampling slower than this, there's a strange thing can happen, all right? And so to ensure you have to be faster than twice of the signal frequency, then you are collecting more, enough of points that you can reconstruct the sinusoid. Because from all this time varying signal, we can decompose the signal into a number of a sinusoidal. So that we call Fourier series or Fourier transform. Okay, hopefully this makes sense. And those who want to it may not make sense to you. You should go to optical illusion, the bandwagon wheel effect. And this is just shocking if you watch the YouTube movie. All right, so let's see. Okay, so here's an example of aliasing, and I have an iPhone. I actually made this movie with my iPhone, which is 30 frames per second. And you know what happens? I realized when we are doing this zoom, the sampling rate is not fast enough that the one I'm watching this is different from what you are watching. So that is a good example of aliasing effect. And unfortunately, when I run this movie, you will not see the same thing as me due to the bandwidth of transmission from my video to your video via Zoom. So because of that, I sent the movie to the Basecamp. Please go download and then watch it. But I'll provide you my explanation, but what you see the video may not be the same. Let me reduce the time, sound a little bit, and let me explain. So when you look at the propeller rotating, it looks slower than it actually is due to aliasing. And then at some point you see the rotational propeller goes backwards. And in fact, it's not true at all. But even the iPhone, and in fact your eye as well, are sampling the nature around you. You can be fooled by this sampling of this fastly changing phenomena. So I strongly urge you to watch this movie at home because we are suffering from aliasing effect that you cannot see exactly the one I'm seeing here. Okay, so yeah, I'm sorry I cannot transmit this one exactly what I see, but let me tell you my point of view for this aliasing. We humans have a also we are sampling outside of the world using our eye, and our eye has a video rate which is limited. So what you see outside of the world, for example, you see the wheel of the wheel running of a car, you are not actually truly seeing what's happening. And I believe this happens all the time, that's why we cannot even trust what we see outside of the world. And you have to think what's actually happening, and you may not even believe what you are seeing. Of course, seeing is believing, but you can be fooled by your seeing because your eye is also a bioinstrument. All right, so let's move on to the next stage that I want to discuss about. Now, let's say you want to develop a bioinstrument which can help understanding, monitoring, and diagnosing disease. And then you have to communicate, or you have to sell, many people would buy it. So how can you characterize and tell the performance of your bioinstrument? Then you need to be able to tell the quality of measurement by quantitative measure. So the first thing you want to say, hey, you measure the true value, you measure some of your biological system, and you have to compare with the true value if it's known. So that we call as simply how accurate your instrument provides. So that's accuracy. And simply accuracy, how can you tell the accuracy? So let's say if you know the true value, okay, we are, then this is a relative difference with respect to true value. So it's a percentage order. So you would say mean of what you measure minus true value, that difference with respect to the true value. So this is a relative deviation times 100 to make it in percent. And another aspect of a quality of what your signal is a reproducibility or repeatability. Whenever you perform an experiment, you get the numbers, you cannot publish it. The reason is you have to prove that you can reproduce your data, not only from you, but also from, in the end, from others can reproduce. So in that aspect, the degree of reproducibility, when we measure multiple times, where the signal output is giving consistent result, that we call precision. And how can you quantify precision? Then easily you can have measured value, the standard deviation, you can use it as a precision, or the ratio of standard deviation with respect to the average value, we call sometimes coefficient of variation. You can use it as a precision. Also, you can hear that, let's say we have a copper, and with the concentration, purity of 99% is 1. But for certain experiments, you want to have a very, very precise one, 99.99999% pure copper as an instrument. What are the differences? The differences are number of significant figure, and this is so important to understand. When you report your data into a report or a journal paper to someone else as a presentation, do not use unnecessary number of numbers which you got from the instrument, because some of them may not be necessary. So in that case, significant figure actually matters. All right, so this picture only shows which ones are more precise. I will get back to this again. So for this, your instrument, you have to tell how small differences you can pick up. That we call as a resolution. Okay, so that's defined as smallest increment that can be resolved in a measurement. We are dealing, as I say, with always collecting signal into a digital form. So in the digital output, we define the resolution as a least significant bit. Here, the bit is digital 0 to 1, 0, 1, 0, 1, and that's a 1 bit, okay? But to express numbers, we can use multiple bits. For example, your color camera has each channel 8 bit, which means one channel, 8 bit can represent how many levels? When you learn about binary, if you have 1 bit, you can express 0, 1. 2 bits, you have 0, 1, 0, 1. So combined 2 times 2 is 4 different levels. Likewise, 8 bits, 2 times 8, 2 times 2 times 8 times, which is 2 to the 8, which is 256 levels. Okay, so when you use 8 bit over 2.56 voltage range, then what is the resolution for that? Because 8 bit can provide you 256 levels, and you divide 2.56 voltage range by this number of levels, you can have one least significant bit. So there, if you calculate that to 10 millivolt, and how it happens is because 8 bit provides you 256 levels. And so the whole range of 2.56 volt divided by this level gives you 10 millivolt per one level, which we define as a resolution. Remember that? So that is 0.1 volt or 0.01 volt or 10 millivolt as a resolution. All right. And when we consider about performance of a bio instrument, from input to output, we have to also consider about the performance. One of the most important questions, how sensitive is your instrument is. And we can define the sensitivity as this. So when the input changes, how sensitively you can detect it. So basically, the input versus output and the slope actually gives you the ratio of delta output change with respect to delta input, and that slope provides you how sensitive your signal is. The other way to say this, we call it as a gain of a system. So that's slope. And so higher sensitivity is in general more desirable. And in this simple case, I showed you as a linear system, then the slope is constant or sensitivity is constant. But remember, whenever you measure something, there's always background. For example, when you're taking picture in your laboratory, let's say fluorescence imaging, the background is supposedly black. But in fact, if you take pictures with a certain amount of exposure time, the background will never be black, okay? So that we call it as an offset. So in reality, the y-axis or the output level many times will not be zero when there is supposedly nothing as an input. So this we call as an offset. And the important thing is this offset is just a simple translation. So it would not affect the slope or sensitivity. So that's why majority of instruments, you will find there's a gain knob and there's offset knob. So you want to adjust the offset when the signal input is zero. So you make sure the output is supposed to be zero. Okay, and then you also change the gain to have enough of sensitivity. But sometimes you realize you don't always have the high sensitivity because it also amplifies your noises as well. Okay. However, this is just a theoretical ways. We have to understand what the real physical instrument, it won't behave exactly this way because the instrument always having saturation. The smallest input, output, and largest output, there's always limit. So that's why I tell this is very important. You have to know the limit of your instruments. Okay. Okay. Curve with the saturation. So it'll be at some point of input signal is high, the output would be saturated. Okay. So in general, this is what happens. 지금 수업 중이어서 나중에 전화 드릴게요.
네, 감사합니다.
Okay, sorry about that. So there's an input, when it's higher, the output is sometimes saturated, which means zero sensitivity or zero slope. So it's very important when you are interpreting your data, always check out if input range is proper linear range. Otherwise, you may be collecting data which is not true. So whenever you have an instrument, check out their working range. And also you want to use it at highest sensitivity. So because more sensitive, it's better. So in general, every system is nonlinear. You are only finding a good, reasonable linear range and to use it as your instrument. So for generalized nonlinear system, you will find the slope is changing depending on the input signal level. So you can define as an instantaneous sensitivity as let's say input sub-zero point, you can have this slope, and that local slope is the sensitivity of that position. Okay, that's more general description. Okay, so I want to discuss generalized Ohm's law, which this one I will, okay, because today the most important thing is I want to discuss about bioinstrument sensitivity and specificity. So I'm gonna skip this. I'll just give you a broad overview, but I actually sent a movie which describes a board exercise. So this way, I think it would be more important for me to focus on what's important. So generalized Ohm's law, you may not be able to find textbook because I made it. How to generally understand dynamical system. So impedance, normally we say resistance. In electrical instrument, the resistance may change depending on the frequency range. So the more generalized expression is impedance. And the driving effort I defined as either mechanical, hydraulic, and electrical system. The driving effort for change I define as a driving effort, and the rate of change. So I define the change component. So here, what I want to emphasize is and let's say in mechanical system, I give a force to change the location or displacement, then driving effort is force. And the change is coming from displacement. And the rate of change, of course, is a velocity. Then how much of work or energy I put into to move this is driving effort times the change, which is force times displacement. And what's the power? The rate of energy consumption is driving effort times rate of change. And what you will realize, this general scheme applies for all the dynamical systems, irrespective of the form. For example, not only mechanical rotation or hydraulic system. Good example is our heart, which is a fluid. By moving with the pressure as a driving effort, we change the volume, and that rate of change is called a volume flow rate. Okay, also it applies to electrical system. The driving effort is the voltage we call a potential. And with this potential difference, we move the charge, and that's the change. And with this, you can actually define energy and power. So this one, I define force, torque, pressure, and electric potential, and change, displacement, angle, and volume, and change. And you will realize how beautiful this underlying principle, which across all these different forms of energy and mechanical, either electrical, even hydraulic system. So with this, I will give you the board exercise, and let's focusing on the evaluation test, which is the most important part of today's lecture. So for disease diagnosis, so I will talk about sensors later on, but the sensors we are measuring, let's say electronic thermometer is having thermal sensor. Pressure transducer to measure blood pressure will have a mechanical sensor. ECG contains electrical sensor. pH meter has a chemical sensor. Pulse oximeter has an optical sensor. That sensing element, they do have this thermal, has thermocouple or thermistor, and a mechanical one has a strain gauge inside, or sometimes piezoelectric sensor. And ECG have electrode, chemical, pH meter also contains electrode, and optical pulse oximeter contains photodiode, and more expensive and sensitive device has PMT or photomultiplier tube, which you already discussed. So let's say about we have developed an instrument to detect coronavirus. Okay, then how can we evaluate this coronavirus detection? Usually, let's say that's a PCR machine. Then you have to consider whether the actual truth of virus or disease present or absent. But your detector, your instrument only spits out a numbers, which you have to define certain threshold. Higher one, hey, you've got this corona, okay? That's we call test positive. And lower, below the threshold, test negative. So somehow you have to, as an engineer, define the threshold, and you have to say to the patient, hey, you've got positive or you've got negative. So that this you have disease and test positive for true positive. You don't have disease, so you have negative result, true negative. However, if you do not have a disease, but the instruments may decide you as a positive, we call false positive. You have a disease, but the instrument somehow you are below the threshold and you've got false negative. This is the most important for decision making because you do not know the truth in general. Okay, so the truth comes with maybe more expensive, more sophisticated technique to define, but this is how test positive and negative is defined, and all different disease and non-disease, or it can be defined as all the positive and negative as all positive means true positive, false positive. Disease now you can see disease is composed true positive and false negative. Likewise, hopefully this makes sense. And for that, now we go back to how to define accuracy of your instrument and how to define accuracy. What does accurate means? Means all the measurement you made, what are the accurate results? Accurate results are actually here true positive, true negative, out of all. Okay, so you can define accuracy this way. And of course, precision is the ability to reproduce, as I say, because whenever you measure, always you will get different results. But the question is how densely located. So this and this and this have high precision, while this has low precision. The mean value is close to center. This is more accurate. This is less accurate. But this one, if you are precise, you can have just offset to make it both precise and accurate. So here I want to define a specificity and sensitivity of your test. And this is super, super important to understand. So why, whenever you want to sell your, let's say, PCR machine to big pharma setting, hey, we've got the best corona detection machine ever. And they will ask you, what are the sensitivity and specificity? Give him the number. This is where you need to know what the sensitivity and specificity mean, because this is critical performance characteristic of a test or assay or bioinstrumentation to diagnose a disease. So let's think of what performance characteristic would be important when you have an instrument. Coronavirus, let's say. So you have test the patient who have a disease, should provide positive value. That's sensitive assay. Okay, how can you convert these words into a formula? Out of all the disease, you should provide true positive. So that's disease. And what does disease mean? True positive plus false negative. You won't have highest sensitivity close to 1, then what that means is you have very low false negative. Okay. What does high sensitivity means then? You have low false negative, which means someone who has a disease will not come out a negative. So that's meaning highly sensitive. On the other hand, you can have another question. Hey, wait a second. I don't have a disease. Let's say I do not have corona, but this damn instrument give me positive results. That caught me like self-isolation to undergo expensive more testing. That's bad. So in that regard, you also think of another aspect. What if when I don't have a disease, the instrument should give me a negative? That we call specific. And specificity you want to define. If I do not have a disease, it should provide me true negative. Okay. So that's specificity. Non-disease, however, composed of true negative plus false positive. So high specificity means you have a very low false positive. And false positive means when I do not have a disease, the instrument should not provide me a positive result. So what this high specificity means, it will not identify me as having disease when I do not have a disease. So why this is important? Let me give you two examples. So when we are dealing with disease such as early stage cancer, if you find it early, you can save your life. In that case, you don't want to miss your disease. So which means you don't have a false negative, or you need high sensitivity. What if the disease is such as, let's say, Alzheimer's disease, okay? Even if I know Alzheimer's disease, there's no proper treatment yet, okay? Then what is important is you don't want to find me as having Alzheimer's disease because it requires me undergoing more expensive evaluation and there's no proper cure yet. Then you don't want to be identified as having disease if you do not have. In that case, specificity is more important. Unfortunately, no instrument will provide both the highest and the highest sensitivity and specificity. There's a trade-off, which I will discuss next time.